My name is Jeff Lee. I'm a product officer at Fiilex. I'm also the head of product development and research for our lighting products. In addition to just the properties of the LED chips themselves, these have to be placed in packages which, because they're selling kind of off the shelf, are somewhat universal. What that means from a mechanical design point of view is that there's a limitation to how they can kind of put things together. Our mechanicals and optics work together. And so in their case, the chips may be small, but the way they route the wires, the kind of platform on which they're built can be large and in an unusual shape. And because of that, they have to design their fixtures to be large to kind of work around that. From a more optical point of view, it's more, the light coming out of the chips has a certain distribution. You basically, what you get from that distribution is what you need to do to shape the light to, shoot on a subject and whatnot. In our case, we actually can shape that distribution at the LED level, and so we get a lot more control from the source. I like to draw an analogy between LED chips and sort of transistors and CPU processing technology. Everyone's wanting to make things smaller, more compact, fit more into a small package. But what happens is that as you get smaller and smaller, you start getting multiple heat sources to be closer and closer together. And that creates a thermal issue. And that's why the whole Pentium craze, Pentium 2, 3, and 4, they made it smaller, but then they realized, oh, it's getting too much heat in a small area. And so they went to multiple cores. So kind of part of that was because they wanted to spread the heat out. In the case of our LEDs, same thing. As you make them smaller, which gives you better mechanical and optical performance, you have to start dealing with heat. Fortunately, our core technology is that not only our electronic board on which the chips are placed is that used to route the signals and power, it's also a really good conductor. And so that same board that routes the electricity is also what does a really good job of conducting heat away from the source. And that's how we're able to pack so much power in such a small package. So if you want to create a hard light, for instance, a really good hard light that we like to use is the sun. And the reason why the sun is so darn good is because it is a point source. It's huge, but it's so far away that it's a little point in the sky. And the rays that travel so far away are basically straight on, okay? And so that's what gives us that hard shadow, that hard light. Same idea with the LED source. If you have a very small source, the rays coming out of that hit the object are also very straight. And so in many ways, if you're looking for a hard source, then you do want to start with a point source. And I think traditionally that's what the industry has been, like light bulbs and small filaments, or HMIs, those are more like point sources. And we're also really comfortable with that because evolutionary, like we're so used to looking at things illuminated by the sun and the shadows from the sun. That's why this whole thing with like multiple shadows is like it's really unnatural because, when in our lives have we had multiple shadows? Ultimately, what we want to do is illuminate a subject which, in space has some dimensions with a light that's tunable and possibly has different colors. And so the idea of the dense matrix is that we can pack strings or LEDs of different colors in a really tight package such that spatially they look like one source. Our goal is to illuminate a subject in space with a uniform color. You don't want it to be red in some area, green in some area, and blue in some other area. And that's what would happen if you started with a source, which is red, green, and blue, like that. What we do is we take these three and we squeeze it together into what we call the dense matrix array. And by squeezing it together in a small package, they mix together better, so it's more like white light. This is more of an issue with LEDs because in the past, LEDs, what they've allowed you to do is have different color chips, different controls, but because of, again, the packaging and electronics around them, they can't be packed so tightly together. And so that's really where the dense matrix array comes in our technology, is that we were able to pack them so close together that they mix well and look like a white source. And not only that, it's also when you're trying to create a source with, in which you're trying to tune the colors, you want to have a lot of control over what color each individual chip is. Traditionally, RGB, yes, that mixes together to make white light, but if you want a really high CRI, then you can have these sharp peaks in the spectral space, which means which is what you would get from a blue, a green, and a red. Instead, what you want to use are phosphors, which kind of re-emit a broader spectrum, and each phosphor has a slightly different spectrum. So at Fiilex, not only do we have, can we tune the chips to be a different power or different intensities, but each of those chips can have a separate phosphor. In fact, we keep around 40 different phosphor recipes in-house, and we tune those specifically for each fixture. Fiilex uses different mixtures of phosphors to get us a tunable full spectrum. What full spectrum means is basically, as you look through the wavelength spectrum, there are not too many peaks. It's pretty smooth and broad across. And the different phosphors that we use have different spectrum. And then as we tune between them, then we can get different mixtures of these spectrum. So as we mix them, we still maintain that broad continuity, that smooth spectrum. Doing a full spectrum that's tunable is really difficult to make because essentially you need different mixtures of phosphors and having different chips turn out with different intensities. And what that means is that your color mixing has to be good, or else you'll see certain color temperature in this part of your light source and a different in this part. And this problem is made even more difficult or challenging in Fresnels because what Fresnels do is they essentially act like a lens, right? And the lens is what they do is the image. So they're taking a pattern and trying to project that pattern somewhere else. And so if your pattern, if you start off with something that is not uniformly mixed, has different color temperatures in different parts of the array, like a bicolor for instance, then as you image that, if you project that across the room, you'll get that same pattern over there. And so this has been a much more challenging thing to do with the Fresnel and lenses than it has been with, for instance, panels or kind of wider angle softer sources. The phosphors tell you what color the chips are, or what kind of colors your light source has, but the way you arrange that on the array is really important too. For instance, if you were to arrange, let's say, for example, I have two different phosphors, half of them on one side and the other half on the other, then you'd get a really clear left and right. And that same pattern would be then projected by your Fresnel lens onto your subject. And so what you want to do is to get uniformity is to mix them together. So you don't have all of them on one side and one on the other. You want to mix them so that they're more uniformly distributed. And so the way we design our array is that we try to kind of almost scramble the chips so that it looks more like a well-mixed source. Typically what we do is we start with our light source, which is our array. And then using computer simulations, we kind of build an optical assembly around that. And then we actually build a real model and then try it out. And then we go back and then we tune the Fresnel until it works perfectly. So we believe that every component in a system has to work well together. And so in the case of our Fresnel, we think that you need a specific Fresnel to be optimized for a certain array. And every time we make a small adjustment to an array, we typically have to adjust the Fresnel as well. And that's why we do a lot of computer simulation and modeling so that we can get this, this kind of mixture or combination correct. Because it's so small in a small area, it looks like a point source. And so if you're trying to make a hard light, we are a good source to start with. Also, because of that good color mixing, we also have a very uniform and smooth profile. You don't get weird colors on the front, weird colors on the rings. You don't get hot spots, things like that. And because we have so many different phosphors and so much phosphor technology and the ability to mix them, we have a wide range, tunable range of spectrums. I'm Jeff Lee with Fiilex. Thanks for watching.